Welcome to the Slumber Lab, where the mysteries of the cosmos unfold gently in the quiet hours. Tonight, we're embarking on a peaceful journey to explore one of the universe's most profound questions. Can planets collapse? It's a question that touches the very foundations of existence, the delicate balance between creation and destruction that governs everything from the smallest pebble to the largest world. As you settle in wherever you are in the world, perhaps curled up in bed or nestled in a favorite chair, I invite you to let your mind wander with me through the cosmic dance of gravity, matter, and time. If you find comfort in these gentle explorations of science, I'd be grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic dreamers. And if by chance this proves too fascinating for sleep, well, at least you'll drift off knowing something new about the grand theatre of space. So take a deep breath, let your thoughts settle like stardust, and let's begin our quiet voyage into the question of planetary collapse. Because in the vast expanse of the universe, even the mightiest worlds are not immune to change. Picture, if you will, a planet floating serenely in the darkness of space. It appears solid, permanent, eternal. But beneath that tranquil surface lies a constant struggle between forces so fundamental they shape the very architecture of reality itself. At the heart of this cosmic tug-of-war is gravity, that gentle but relentless force that pulls all matter toward itself with patient persistence. Gravity is both creator and destroyer in the cosmic story. It's the force that gathers cosmic dust into planets, that holds atmospheres close to their worlds, that keeps moons dancing around their planetary partners. Yet this same force, given the right circumstances, can become an agent of collapse, drawing matter inward with such intensity that even the most massive planets cannot resist. The story of planetary collapse begins with understanding what physicists call gravitational equilibrium. Imagine a planet as a delicate balance, like a dancer frozen in perfect pose. On one side, gravity pulls everything inward, trying to compress the world into an ever smaller sphere. On the other side, various forces push outward. The pressure of hot gases, the structural integrity of rock and metal, the thermal energy generated by radioactive decay deep within the planetary core. For most planets, this is a dance that can continue for billions of years. Earth has maintained this balance for over 4 billion years, our homeworld neither expanding into space nor collapsing inward. But this equilibrium is not guaranteed forever, and it's certainly not universal. Some worlds, under the right conditions, can find themselves losing this cosmic battle against their own gravity. The mathematics of this process are both elegant and sobering. There exists what scientists call the Jeans mass, named after physicist Sir James Jeans, which represents a critical threshold. When a collection of matter exceeds this mass, gravity becomes the dominant force, and collapse becomes not just possible, but inevitable. It's like a cosmic point of no return, where the universe itself decides that a particular collection of matter has grown too large to remain stable. For most planets in our solar system, this threshold is safely distant. Earth, Mars, Jupiter, even the mighty gas giants, all exist well within the bounds of stability. But in the broader universe, where planets come in sizes and compositions we're only beginning to understand, the story becomes more complex and sometimes more dramatic. Consider the gas giants that orbit very close to their stars, worlds that astronomers call hot Jupiters. These massive planets, sometimes several times larger than Jupiter itself, orbit their stars so closely that their atmospheres are heated to thousands of degrees. In this extreme environment, the delicate balance between gravity and outward pressure can shift dramatically. The intense heat causes the atmosphere to expand, but it also creates conditions where portions of that atmosphere can be stripped away entirely, particle by particle, escaping into space like a slow-motion explosion, played out over millions of years. This process, called atmospheric escape, represents one form of planetary collapse. Not the sudden, catastrophic implosion we might imagine, but a gradual dissolution, like a sugar cube slowly dissolving in cosmic tea. The planet doesn't disappear overnight, but over geological timescales, it can lose so much of its mass that it transforms from a gas giant into something entirely different, perhaps a small rocky core orbiting naked in space. But atmospheric escape is just one pathway to planetary transformation. The universe has other, more dramatic methods of reshaping worlds. In the dense stellar nurseries where new stars are born, we find evidence of a completely different type of planetary collapse, one that occurs not through slow erosion, but through rapid, direct gravitational collapse. Recent observations of young stellar systems have revealed something remarkable. In the swirling disks of gas and dust that surround newborn stars, astronomers have detected spiral patterns and density enhancements that suggest the disk itself is becoming gravitationally unstable. These are not the slow, steady processes of traditional planet formation, where dust grains gradually stick together over millions of years. Instead, these are regions where the disk material is collapsing directly into planetary mass objects in what might be only thousands of years. This process, called gravitational instability, represents a kind of cosmic shortcut to planet formation. But it's also inherently unstable. Planets born through this rapid collapse process often find themselves in precarious situations, their orbits unstable, their internal structure still settling. Many of these worlds may not survive their violent birth process, either falling into their parent star or being ejected entirely from their solar system. The AB Auriga system, located about 520 light-years from Earth, provides us with a remarkable window into this process. This young star, only a few million years old, is surrounded by a disk showing clear signs of gravitational instability. Astronomers have observed spiral arms, density enhancements, and what appears to be a massive object embedded within the disk itself. It's like watching planetary collapse and formation happening in real time, though on timescales so vast that real time means millions of years. What makes AB Auriga particularly fascinating is that it challenges our understanding of what's possible in planetary formation. The disk around this star is massive enough and unstable enough that it could fragment into multiple planetary mass objects through direct gravitational collapse. But these same conditions that allow for rapid planet formation also make the system highly unstable. Many of the objects formed through this process may not survive long enough to become stable, long-lived planets. This brings us to one of the most sobering aspects of planetary collapse: the creation of rogue planets. These are worlds that have been ejected from their birth systems, left to wander the galaxy alone, no longer warmed by the light of a parent star. Current estimates suggest there may be billions, perhaps trillions, of these homeless worlds drifting through the Milky Way, silent witnesses to cosmic violence. The ejection process that creates rogue planets is itself a form of planetary system collapse. In the early stages of solar system formation, when multiple massive planets are still settling into their final orbits, gravitational interactions can become chaotic. Computer simulations show that these interactions often result in one or more planets being flung out of the system entirely, their orbits disrupted so violently that they escape the gravitational embrace of their parent star. Binary star systems, those cosmic partnerships where two stars orbit around each other, are particularly efficient at creating rogue planets. The complex gravitational dance between two massive stars creates a constantly shifting gravitational landscape that can destabilize planetary orbits. Research suggests that binary systems may eject between 2 and 7 planets per system, each one a world suddenly condemned to eternal night. The fate of these rogue planets is both melancholy and magnificent. Suddenly cut off from the warmth of their parent star, they begin a long, slow, cooling process. Any atmospheres they possessed gradually freeze out, forming exotic ices on their surfaces. Any moons they might have had become their only companions in the darkness. Yet these worlds continue to exist, carrying within them the geological record of their birth, the chemical signatures of the stellar nursery where they formed. But perhaps the most poetic form of planetary collapse comes not from violence or instability, but from the gentle, inevitable process of stellar evolution. Every star, including our own sun, will eventually exhaust the nuclear fuel that powers its core. When that happens, the star begins to expand, growing into a red giant that can engulf the inner planets of its system. Our sun, that reliable companion that has warmed Earth for billions of years, will one day grow so large that it extends beyond the orbit of Mars. Mercury and Venus will be consumed entirely, their rocky bodies vaporized in the expanding stellar atmosphere. Earth itself may be engulfed, or it may survive as a charred, lifeless world orbiting the dying ember of what was once our vibrant star. This process represents the ultimate form of planetary collapse, not through gravitational instability or atmospheric escape, but through the simple passage of time and the inevitable evolution of stars. It's a reminder that even the most stable, long-lived planets exist within a cosmic context that is constantly changing. Yet even in this seemingly terminal process, there are elements of hope and renewal. When a star sheds its outer layers to become a white dwarf, it enriches the surrounding space with heavy elements forged in its nuclear furnace. These elements, scattered into the cosmic medium, become the building blocks for new generations of stars and planets. The collapse of one world becomes the foundation for countless others. The story becomes even more complex when we consider planets in multiple star systems. The HD 1131399 system, though its planetary candidate was later determined to be a background star, represents the kind of gravitational complexity that makes long-term stability extremely difficult. In systems with 3 or more stars, the gravitational interactions become so complex that they can destabilize planetary orbits over timescales of millions of years. Even if a planet manages to form in such a system and maintain a stable orbit during the main sequence lifetime of its stars, the eventual evolution of those stars into giants can completely disrupt the gravitational balance. The result is often the ejection of any remaining planets, another pathway to the creation of rogue worlds. The concept of planetary collapse extends beyond individual worlds to entire planetary systems. Tidal disruption events, where a star passes too close to a supermassive black hole, can scatter or destroy all the planets in a system. Stellar collisions, supernovae, and gamma-ray bursts can sterilize or obliterate planetary surfaces. The universe, for all its beauty and complexity, can be a harsh place for worlds. But perhaps the most subtle form of planetary collapse is the one that happens not through cosmic violence, but through the simple loss of a planet's ability to maintain its identity. Planets that lose their atmospheres, their magnetic fields, their geological activity, gradually become something less than they once were. Mars, with its thin atmosphere and lack of global magnetic field, may represent a world in the slow process of collapse, not into a black hole or ejection into space, but into geological death. Yet even this process is not necessarily permanent. Venus, despite its hellish surface conditions, maintains a thick atmosphere and active geology. Some worlds that appear geologically dead may simply be in dormant phases, waiting for some cosmic event to reawaken their internal fires. The study of exoplanets, planets orbiting other stars, has revealed just how diverse and dynamic planetary systems can be. We've discovered worlds that orbit so close to their stars that their surfaces are molten rock, planets where it rains liquid metal, gas giants with densities lower than water that are slowly evaporating into space. Each of these represents a different pathway in the complex story of planetary formation, evolution, and potential collapse. Some of the most extreme examples of planetary collapse may be happening right now in distant star systems. Planets being tidally disrupted as they spiral into their parent stars, worlds being stripped of their atmospheres by stellar winds, entire planetary systems being reorganized by the gravitational influence of passing stars. The universe is a dynamic place, constantly reshaping itself on scales both vast and intimate. As we contemplate these cosmic processes from our own seemingly stable world, it's worth remembering that Earth itself is not immune to change. Our planet's magnetic field, which protects us from harmful solar radiation, has reversed many times in the past and will likely reverse again. Our atmosphere has undergone dramatic changes throughout Earth's history. The continents themselves drift slowly across the surface, constantly reshaping the geography of our world. In the very long term, Earth faces its own forms of potential collapse. The gradual cooling of our planet's core will eventually shut down the magnetic field permanently. The slow increase in the sun's luminosity will eventually make Earth too hot for liquid water. And ultimately, the sun's evolution into a red giant will present our world with the same challenges faced by countless other planets throughout the galaxy. But these are processes that unfold over timescales so vast they dwarf human civilization. The collapse of planets, whether through gravitational instability, atmospheric escape, or stellar evolution, typically happens over millions or billions of years. From our perspective, these are geological eternities, timescales on which entire species evolve and disappear, on which mountain ranges rise and erode away to nothing. This perspective can be both humbling and comforting. Humbling because it reminds us of our place in a universe far larger and more dynamic than our daily experience suggests. Comforting because it suggests that the processes that shape planets, even the most dramatic ones, unfold with a patience that allows for adaptation, evolution, and renewal. The question of whether planets can collapse is ultimately a question about the nature of stability in the universe. Nothing is permanent, not worlds, not stars, not even galaxies. Everything exists in a state of dynamic equilibrium, balanced between forces that would tear it apart and forces that hold it together. Sometimes that balance shifts, and what was stable becomes unstable. What was solid becomes scattered. What was whole becomes something entirely different. Yet in this cosmic impermanence, there is also continuity. The atoms that make up collapsed planets don't disappear. They become part of new worlds, new stars, new possibilities. The gravitational collapse that destroys one planetary system can trigger the formation of another. The universe recycles itself endlessly, finding new ways to organize matter and energy into complex, beautiful structures. As you drift towards sleep tonight, perhaps you can take comfort in knowing that you are part of this vast cosmic story. The elements in your body were forged in the hearts of ancient stars, scattered into space by stellar winds and supernova, gathered into the disk of gas and dust that would eventually become our solar system. You are made of the same materials that form planets, that collapse into black holes, that shine in distant galaxies. The story of planetary collapse is ultimately a story about change, about the constant transformation that characterizes everything in the universe. Planets can indeed collapse through gravitational instability, atmospheric escape, tidal disruption, or stellar evolution. But these processes, dramatic as they may be, are part of a larger cycle of creation and destruction that has been ongoing for billions of years and will continue for billions more. In this cosmic perspective, collapse is not an ending, but a transformation. Not a failure, but a phase transition. Not death, but metamorphosis. The universe is constantly reinventing itself, finding new ways to arrange matter and energy, new possibilities for complexity and beauty. Even in collapse, there is creativity. Even in destruction, there is renewal. So yes, planets can collapse, but in their collapse, they become part of something larger, something that transcends individual worlds and encompasses the entire cosmic story of which we are all part. And in that story, every ending is also a beginning. Every collapse the foundation for something new and wonderful yet to come. Now that we've seen how planetary systems can be torn apart by catastrophic events, let's turn our attention to a quieter, but no less fascinating question. What happens when these cosmic disruptions create something entirely new? Because while we've explored the dramatic collapses that can destroy entire worlds, the universe has another trick up its sleeve: the ability to forge new planets from the ashes of destruction. Think of it this way. Every ending in the cosmos is also a beginning. When a star goes supernova, it doesn't just destroy nearby planets. It scatters heavy elements across space, the very ingredients needed to build new rocky worlds. When binary stars tear apart each other's atmospheres, that material doesn't simply vanish. It can form new disks of matter, new opportunities for planetary birth. Even when entire planets are ejected into the cold darkness of interstellar space, they carry with them the potential for something unexpected. This brings us to one of the most remarkable discoveries in modern astronomy: second-generation planetary systems. These are worlds that form not from the pristine gas and dust of a young stellar nursery, but from the recycled remains of previous cosmic catastrophes. It's a bit like nature's ultimate recycling program, where the debris of one world becomes the foundation for another. Consider pulsar planets, some of the strangest worlds we've ever discovered. Pulsars are the incredibly dense, rapidly spinning remnants of massive stars that have exploded as supernovae. These cosmic lighthouses emit beams of radiation that sweep across space like the beam of a lighthouse, creating the regular pulses that give them their name. For decades, astronomers assumed that no planet could possibly survive the violent death of its parent star, let alone form afterward. But in 1992, astronomers made a startling discovery around a pulsar called PSR B11257+12. Not only were there planets orbiting this stellar corpse, but there were multiple worlds, each roughly the size of Earth. These planets couldn't have survived the supernova that created the pulsar. They must have formed afterward, from the debris expelled during the star's death throes. It was like finding a garden growing in the crater of a volcano. These pulsar planets represent a form of planetary resurrection. The supernova that destroyed the original planetary system also provided the raw materials for a new one. Heavy elements forged in the star's core and scattered by the explosion condensed into new worlds, orbiting the dense neutron star that remained. It's a process that takes the most violent event in a star's life and transforms it into an opportunity for planetary rebirth. But pulsar planets aren't the only example of cosmic recycling. White dwarf stars, the hot, dense cores left behind when sun-like stars shed their outer layers, also show signs of planetary resurrection. Many white dwarfs have atmospheres contaminated with heavy elements: silicon, magnesium, iron, calcium, that should have long since sunk into the star's interior under the influence of its intense gravity. The presence of these elements tells us that rocky material is actively falling onto the white dwarf, possibly from asteroids or even small planets that formed from the debris of the star's planetary nebula phase. Some of these white dwarf systems show regular dimming patterns that suggest intact objects, possibly small planets or large asteroids, are orbiting very close to the stellar remnant. These objects might be the survivors of the original planetary system, somehow managing to avoid destruction during their star's giant phase. Or they could be new bodies that formed from the scattered remains of worlds that weren't so fortunate. The process of planetary formation around stellar remnants follows many of the same principles we see in young stellar systems, but with some crucial differences. The raw materials are different. Instead of pristine hydrogen and helium with a sprinkling of heavier elements, these second-generation disks are rich in the products of stellar nucleosynthesis. Silicon, oxygen, magnesium, iron. All the elements needed to build rocky worlds are present in abundance. But there's also a dark side to this cosmic recycling. The environments around stellar remnants are harsh, bathed in intense radiation and gravitational forces that would be lethal to any life as we know it. The pulsar planets orbiting PSR B12 57+12, for instance, are bombarded with radiation levels millions of times higher than Earth experiences. Any atmosphere they might have had would be stripped away almost instantly, leaving behind airless, irradiated worlds more hostile than anything in our solar system. Yet even in these extreme environments, the process of planetary formation continues. Computer simulations suggest that debris disks around white dwarfs could form small rocky planets within just a few million years, a blink of an eye in cosmic terms. These worlds would be born into a universe very different from the one that saw their predecessors, orbiting the cooling remnant of a star that once sustained an entire planetary family. The story of planetary resurrection extends beyond individual stellar systems. On galactic scales, the heavy elements produced by stellar death and dispersed by supernovae and stellar winds become incorporated into new generations of stars and planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these were forged in the nuclear furnaces of ancient stars and scattered into space by stellar death. In a very real sense, we are all made from the ashes of worlds that died billions of years ago. This cosmic recycling process has been going on for most of the universe's history. The first generation of stars, born from the pristine hydrogen and helium left over from the Big Bang, could only form gas giant planets. Rocky worlds like Earth were impossible because the heavy elements needed to build them simply didn't exist yet. It was only after these first stars lived their lives and died, scattering newly forged elements into space, that the universe became capable of forming terrestrial planets. Each subsequent generation of stars and planets has been enriched by the deaths of its predecessors. 6 billion years ago was already seasoned with the remnants of countless stellar deaths, supernovae that exploded, white dwarfs that cooled, neutron stars that spun down into darkness. Our Earth, our bodies, our entire existence is built from this cosmic recycling, this endless process of death and rebirth that has shaped the universe for over 13 billion years. But perhaps the most intriguing aspect of planetary resurrection is what it suggests about the resilience of the cosmos itself. Even the most catastrophic events, the explosion of a massive star, the collision of neutron stars, the consumption of planets by their dying parent stars, cannot permanently halt the process of planetary formation. The universe seems almost determined to continue creating new worlds, new opportunities for complexity, and perhaps even life to emerge. This resilience extends to the possibility of life itself surviving cosmic catastrophes. While the pulsar planets we've discovered are almost certainly sterile, bathed in lethal radiation, other forms of planetary resurrection might be more hospitable. White dwarf systems, for instance, could potentially harbor habitable zones where temperatures are just right for liquid water, though any such worlds would be very close to their stellar remnant and tidally locked, with one side in permanent day and the other in eternal night. More intriguingly, some scientists have speculated about the possibility of life surviving the transition from a normal star to a white dwarf. As a sun-like star evolves into a red giant, its habitable zone moves outward, potentially making previously frozen worlds warm enough for life. Moons of gas giants, previously too cold to support biology, might find themselves in a brief window of habitability as their star swells and brightens. When the star finally sheds its outer layers and becomes a white dwarf, the habitable zone contracts dramatically, but it doesn't disappear entirely. Any worlds that manage to survive the red giant phase might find themselves in a stable, if alien, environment where they could potentially support life for billions of years. White dwarfs cool very slowly, providing a steady, long-term energy source that could sustain biospheres for longer than main sequence stars like our Sun will shine. These scenarios remain highly speculative, but they illustrate an important point. The universe's capacity for renewal extends beyond mere planetary formation to the possibility of biological resurrection as well. Life, like the planets that host it, might be more resilient than we imagine, capable of surviving and even thriving in the aftermath of cosmic catastrophe. The study of planetary resurrection also provides crucial insights into the long-term future of our own solar system. In about 5 billion years, our Sun will begin its evolution toward becoming a red giant, eventually shedding its outer layers to become a white dwarf. The inner planets, Mercury, Venus, Earth, and possibly Mars, will likely be destroyed in this process, their atoms scattered into space. But that scattered material won't simply disappear. Some of it will fall onto the newly formed white dwarf, creating the kind of heavy element contamination we observe in other white dwarf atmospheres. Some might form new asteroids or small planets in orbit around our Sun's stellar remnant. And some will be dispersed into the interstellar medium, where it will eventually become incorporated into new generations of stars and planets. In this sense, Earth's ultimate fate isn't destruction, but transformation. The atoms that make up our world, our biosphere, and ourselves will continue their cosmic journey long after our planet has been reduced to its constituent elements. They will help build new worlds around new stars, carrying forward the chemical legacy of our solar system into the far future. This perspective transforms our understanding of planetary collapse from a tale of endings to one of beginnings. Every world that falls into its star, every planet stripped of its atmosphere, every moon shattered by tidal forces contributes to the universe's ongoing experiment in world building. The cosmos learns from each catastrophe, incorporating the lessons of destruction into new cycles of creation. As we drift toward the end of our exploration of planetary collapse, we're left with a profound realization. In the universe, nothing is ever truly lost. Matter and energy are conserved, constantly recycled through an endless series of cosmic transformations. The same atoms that once formed the first rocky planets in the early universe might now be part of distant worlds, orbiting alien suns. And billions of years from now, they might be incorporated into planets we can't even imagine. This is perhaps the most comforting truth about planetary collapse. It's not an ending, but a transition. Every world that dies gives birth to new possibilities, new chances for complexity and beauty to emerge. The universe is not running down towards some final, lifeless equilibrium, but continuously reinventing itself, finding new ways to organize matter and energy into ever more intricate and wonderful forms. So while planets can indeed collapse, consumed by their stars, stripped by stellar winds, ejected into the void, or shattered by cosmic collisions, they also participate in something much grander, the universe's endless capacity for renewal and rebirth. Or, we've touched on how planets can face destruction through violent cosmic events and ejection from their systems. But there's another fascinating pathway to planetary collapse that unfolds more gradually, almost like a slow-motion dance of destruction. Tonight, Let's explore how planets can literally fall apart from the inside out, succumbing to forces that have been quietly working against them for billions of years. Picture this. You're floating in space, watching a planet that looks perfectly normal from the outside. Its atmosphere glows softly in the starlight. Its surface appears stable, maybe even habitable. But deep within its core, something fundamental is changing. The delicate balance that has held this world together for eons is beginning to shift. And what you're witnessing is the early stages of a planetary death that could take millions of years to complete. This is the story of gravitational collapse, and it's far more common than you might think. Every planet, including our own Earth, exists in a constant state of tension between the forces trying to pull it apart and those holding it together. It's a cosmic balancing act that's been playing out since the moment these worlds first formed, and sometimes that balance tips in the wrong direction. Let's start with something that might surprise you. The very force that created planets is also the force that can destroy them. Gravity, that gentle pull that keeps your feet on the ground and the moon in orbit around Earth, becomes a monster when it grows too strong. You see, gravity doesn't just hold things together, it also wants to crush everything down to the smallest possible point. The only reason planets don't collapse into tiny, incredibly dense balls is because other forces push back against gravity's relentless squeeze. In rocky planets like Earth, it's the electromagnetic forces between atoms that provide this resistance. The atoms in rock and metal refuse to be compressed beyond a certain point, creating what physicists call degeneracy pressure. It's like having billions of tiny springs throughout the planet, all pushing outward against gravity's inward pull. As long as these forces remain balanced, the planet maintains its shape and structure. But what happens when that balance breaks down? Sometimes a planet can simply grow too massive for its own good. As more and more material accumulates, whether from asteroid impacts, the capture of smaller moons, or the gradual accretion of cosmic dust, the gravitational force becomes overwhelming. The electromagnetic forces that once held the planet's structure intact begin to buckle under the pressure. This process doesn't happen overnight. It might take millions or even billions of years for a planet to slowly compress and deform. But once it begins, it becomes increasingly difficult to stop. The planet's core grows denser and hotter as it's compressed, which can trigger new chemical reactions and phase changes in the materials deep underground. What was once solid rock might transform into exotic forms of matter that behave in completely unexpected ways. Scientists have discovered that there are actually several critical mass thresholds that determine a planet's fate. Cross the first threshold, and a rocky planet might begin to develop a thick, crushing atmosphere as its gravity becomes strong enough to hold onto lighter gases that would normally escape to space. This is what happened to Venus, though in that case, the thick atmosphere created a runaway greenhouse effect rather than direct gravitational collapse. Cross the second threshold, and something more dramatic occurs. The planet becomes massive enough that its gravity begins to compress hydrogen gas into liquid, then into metallic hydrogen, a strange state of matter that only exists under extreme pressure. This is the realm of gas giants like Jupiter and Saturn, worlds so massive that they've fundamentally changed the nature of the materials within them. But there's a third threshold, and this one leads to true planetary collapse. When a planet grows beyond roughly 13 times the mass of Jupiter, its core becomes so compressed that it begins to undergo nuclear fusion. At this point, the object is no longer really a planet at all. It's become a brown dwarf, a failed star that glows with its own internal heat, but never quite managed to ignite into a full stellar furnace. The transition from planet to brown dwarf is one of the most spectacular forms of planetary collapse imaginable. The world literally tears itself apart from the inside as nuclear reactions begin in its core. The outer layers may be blown away in massive stellar winds, while the remaining material settles into an entirely new configuration. What was once a solid world becomes a roiling ball of plasma and exotic matter. But gravitational collapse isn't the only way planets can fall apart from within. There's another, more subtle process that can doom a world over geological timescales: atmospheric escape. Every planet with an atmosphere is constantly losing small amounts of gas to space. Molecules in the upper atmosphere occasionally gain enough energy to break free from the planet's gravitational pull and drift away into the cosmic void. For most planets, this loss is negligible, barely noticeable over billions of years. Earth loses only a few hundred tons of atmosphere per day, a tiny fraction of our planet's total atmospheric mass. But under certain conditions, atmospheric escape can accelerate dramatically, leading to what scientists call hydrodynamic escape, where the atmosphere literally boils away into space. This process is particularly devastating for planets orbiting close to their stars. The intense radiation and stellar wind can strip away atmospheric particles at an alarming rate, like cosmic sandblasting. Mars likely lost much of its atmosphere this way, transforming from a world that might once have supported liquid water into the cold, thin-air desert we see today. Even more dramatically, some exoplanets discovered by our space telescopes appear to be in the process of complete atmospheric collapse right now. These hot Jupiters, gas giant planets that orbit extremely close to their stars, are literally evaporating before our eyes. Astronomers have detected vast comet-like tails of gas streaming away from these worlds, the remnants of atmospheres being torn apart by stellar radiation. The HD 229458b system provides a haunting example of this process. This planet, located about 150 light-years from Earth, is losing roughly 10,000 tons of atmosphere every second. At this rate, the entire gaseous envelope that makes it a gas giant will be gone in just a few billion years, leaving behind only a small, rocky core. It's planetary death in slow motion, visible across interstellar distances. But perhaps the most unsettling form of internal planetary collapse involves the breakdown of a world's magnetic field. A planet's magnetic field acts like an invisible shield, deflecting harmful radiation and preventing the solar wind from directly interacting with the atmosphere. When this magnetic shield fails, the consequences can be catastrophic. Mars offers a sobering example of what happens when a planet loses its magnetic protection. Scientists believe that Mars once had a strong magnetic field generated by a liquid, convecting core. But as the planet cooled over billions of years, this internal dynamo gradually shut down. Without its magnetic shield, Mars became vulnerable to the solar wind, which slowly but steadily stripped away its atmosphere and any liquid water that might have existed on its surface. The collapse of a planetary magnetic field can happen in several ways. Sometimes the planet's core simply cools and solidifies, ending the convective motions that generate the magnetic field. Other times, catastrophic impacts or internal upheavals can disrupt the delicate balance of the core's dynamics. In rare cases, the magnetic field might even flip or reverse, leaving the planet temporarily unprotected during the transition. On Earth, we've seen hints of what magnetic field collapse might look like. Our planet's magnetic field has weakened by about 10% over the past 150 years, and the magnetic North Pole has been wandering across the Arctic at an accelerating pace. While this is likely part of a natural cycle that could lead to a magnetic field reversal, it reminds us how dependent we are on this invisible protective barrier. There's also the fascinating case of tidal collapse, where a planet is literally torn apart by the gravitational forces of a nearby object. This can happen when a planet ventures too close to its star, or when it passes within the Roche limit of a massive companion. The Roche limit is the distance at which tidal forces overcome the planet's own gravity, causing it to disintegrate into a ring of debris. We can see examples of tidal disruption throughout our solar system. Saturn's rings are thought to be the remains of moons that wandered too close to the giant planet and were torn apart by tidal forces. Some of Jupiter's smaller moons show signs of tidal stress, with long fractures and ridges carved into their surfaces by the constant flexing caused by the planet's immense gravity. The process of tidal collapse is both gradual and sudden. A planet approaching its doom might spend thousands of years slowly deforming, developing massive tidal bulges, and experiencing increasingly violent earthquakes as internal stresses build up. Then, at the critical moment, the world simply comes apart, breaking into chunks that spread out into a ring around the massive object that destroyed it. But here's where the story takes an unexpected turn. Planetary collapse isn't always the end of the story. In the grand cosmic cycle of destruction and creation, the death of one world can lead to the birth of others. The debris from collapsed planets doesn't simply vanish. It becomes raw material for new planetary formation. When a planet is torn apart by tidal forces, the resulting ring of material can eventually coalesce into new, smaller moons. When atmospheric escape strips away a gas giant's envelope, it might reveal a rocky core that could, under the right conditions, develop its own atmosphere and become a terrestrial world. Even the exotic matter created in the cores of collapsing superplanets might eventually be recycled into new stellar systems when the parent star dies and spreads its enriched material into space. This cosmic recycling extends to the most extreme cases of planetary collapse. When massive planets become brown dwarfs, they're not just ending one phase of existence, they're beginning another. Brown dwarfs can persist for trillions of years, slowly cooling and fading, but remaining active participants in the cosmic dance. Some might even acquire planetary companions of their own, becoming the centers of exotic stellar systems unlike anything we see around normal stars. The study of planetary collapse has revealed something profound about the nature of worlds. They're not permanent fixtures in the universe, but temporary arrangements of matter that exist in a constant state of tension between creation and destruction. Every planet is engaged in an ongoing battle against the forces that would tear it apart, and sometimes those forces win. Yet there's something almost poetic about planetary collapse when viewed from the perspective of deep time. These processes, which seem catastrophic from our human viewpoint, are simply part of the universe's natural cycle of renewal. Matter is never truly destroyed, only transformed. The atoms that once formed the core of a collapsed planet might eventually find themselves in the atmosphere of a newly formed world, or in the body of a living creature on some distant shore. This perspective doesn't diminish the drama of planetary collapse, but rather places it in a broader context. We're witnessing not just destruction, but transformation on the grandest possible scale. The universe is constantly reinventing itself, taking apart old structures and building new ones, experimenting with different arrangements of matter and energy. As we drift toward the end of our exploration of internal planetary collapse, it's worth remembering that these processes are happening right now throughout the galaxy. Somewhere, a planet is slowly losing its atmosphere to space. Somewhere else, a world is being torn apart by tidal forces. And somewhere beyond that, new planets are forming from the debris of old ones, continuing the endless cycle of cosmic death and rebirth. The next time you look up at the night sky, remember that you're not just seeing points of light, but participants in an ongoing story of transformation that spans billions of years. Some of those stars might harbor planets in the process of collapse, while others might be nurturing the birth of new worlds from the ashes of the old. In this grand cosmic perspective, planetary collapse becomes not a tale of endings, but of continuity. A reminder that in the universe, nothing is permanent, but everything is connected. The story of planets is ultimately the story of matter itself, finding new forms, new arrangements, new ways to exist in the vast theatre of space and time. Now we dive deeper into the cosmic drama of destruction and rebirth, where entire worlds don't simply vanish, but transform in ways that challenge our understanding of permanence itself. The story of planetary collapse isn't just about endings, it's about the universe's relentless creativity in recycling matter and energy across scales so vast they humble our imagination. Binary star systems emerge as particularly efficient architects of planetary chaos. In these cosmic dances, two stars orbit each other in gravitational tangos that can persist for millions of years before something shifts. When stellar companions grow too close, or when a third star wanders into the neighborhood, the delicate orbital mechanics that once kept planets safely in their lanes suddenly become unpredictable. Computer simulations reveal that circumbinary planets, those brave worlds orbiting both stars in a binary system, face ejection rates that dwarf those around single stars. Each binary system can fling between 2 to 7 Earth-mass planets into the cosmic void, creating a steady stream of wandering worlds. These rogue planets represent one of the most profound forms of planetary collapse, not through destruction, but through exile. Current estimates suggest there may be 20 rogue planets for every star in our galaxy. If the Milky Way contains 200 billion stars, we're looking at potentially 4 trillion homeless worlds drifting through interstellar space. These aren't failed planets or cosmic debris, they're fully formed worlds that once knew the warmth of stellar light, that perhaps harbored atmospheres and maybe even primitive life before being cast into the eternal night between stars. The ejection process itself reveals the fundamental instability lurking within every planetary system. During the first few million years after formation, when protoplanetary disks still swirl with dust and gas, gravitational interactions between forming planets can become chaotic. Like cosmic billiard balls, these worlds scatter each other's orbits until some achieve escape velocity and flee their birth systems forever. The simulations show that most ejections occur while the parent star is still young, suggesting that planetary systems undergo a violent shakeout period before settling into their mature configurations. But stellar evolution offers an even more dramatic pathway to planetary collapse. As stars age, they don't simply fade away quietly. Low-mass stars, like our Sun, will eventually expand into red giants, their outer layers swelling to hundreds of times their original size. Any planets in close orbits face inevitable consumption, literally swallowed by their expanding parent star. This isn't a quick process. The red giant phase can last hundreds of millions of years, during which planets experience steadily increasing temperatures as the stellar surface approaches. The physics of this stellar cannibalism are both beautiful and terrifying. As a planet spirals into its expanding star, tidal forces begin to tear it apart long before it reaches the stellar surface. Rocky worlds fragment into streams of debris that rain down onto the star, temporarily enriching its outer layers with heavy elements. Gas giants fare slightly better. Their massive atmospheres can sometimes survive partial engulfment, creating complex interactions between planetary material and stellar plasma. Even more exotic are the fates awaiting planets around massive stars. When stars more than 8 times the mass of our Sun reach the end of their lives, they don't become gentle red giants, they explode as supernovae. The explosion itself releases more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. Any planets within several light years of such an explosion face instant vaporization, their constituent atoms blasted apart and scattered across interstellar space. Yet even this ultimate destruction serves the universe's creative purposes. The heavy elements forged in stellar cores and dispersed by supernovae become the building blocks for new generations of planets. The carbon in your body, the oxygen you breathe, the iron in your blood, All were created in the nuclear furnaces of dying stars and distributed through space by these cosmic explosions. In this sense, planetary collapse becomes part of an endless cycle of cosmic recycling. Perhaps nowhere is this cycle more evident than in the strange worlds orbiting pulsars. These neutron stars, the collapsed cores of exploded massive stars, shouldn't have planets at all. The supernova that created them should have obliterated any pre-existing worlds. Yet several pulsar planets have been discovered, apparently formed from the debris of the explosion itself. These second-generation worlds, born from the ashes of their predecessors, represent a kind of cosmic reincarnation where destruction becomes creation. The mechanisms of planetary collapse extend beyond stellar violence to include more subtle but equally inexorable processes. Atmospheric escape, driven by stellar radiation and solar wind, can slowly strip away a planet's gaseous envelope over geological time. Mars likely lost much of its original atmosphere this way, transforming from a potentially habitable world into the cold, thin-air desert we see today. Venus, despite retaining its atmosphere, may have lost vast oceans to a runaway greenhouse effect, another form of planetary transformation that borders on collapse. Even our own Earth isn't immune to these processes. The gradual brightening of the sun as it ages will eventually make our planet uninhabitable, boiling away the oceans and stripping the atmosphere. This thermal death awaits us in roughly 1 billion years, though other catastrophes might intervene first. The eventual collision between our Milky Way galaxy and the Andromeda galaxy in 4 billion years could gravitationally disrupt our solar system, potentially ejecting Earth into intergalactic space. But perhaps the most unsettling aspect of planetary collapse is how it reveals the fundamental impermanence of everything we consider stable. The continents beneath our feet, the atmosphere we breathe, the magnetic field that shields us from cosmic radiation, all exist in delicate balance. Disruptions to any of these systems could trigger cascading failures that render a planet uninhabitable or even physically disrupted. Climate collapse represents one such vulnerability. Venus serves as a stark reminder that planets can transition between dramatically different states. Billions of years ago, Venus might have been temperate enough for liquid water. Today, its surface temperature approaches 900 degrees Fahrenheit, hot enough to melt lead. This transformation didn't require external catastrophe, just the gradual accumulation of greenhouse gases and the loss of water vapor to space. Similarly, magnetic field collapse can expose a planet to the full fury of its star's radiation and particle wind. Mars lost its global magnetic field early in its history, allowing the solar wind to gradually strip away its atmosphere. Without this protective shield, any surface life would have faced increasing exposure to harmful radiation, potentially driving any existing biosphere into extinction or underground. The study of exoplanets has revealed even more exotic forms of planetary collapse. Hot Jupiters, gas giants orbiting extremely close to their stars, experience atmospheric temperatures exceeding 2,000 degrees Fahrenheit. These worlds are literally evaporating, their atmospheres boiling off into space and creating comet-like tails of escaping gas. Over time, these planets may be reduced to bare rocky cores, the remnants of once massive worlds stripped down to their essential elements. Tidal disruption represents another spectacular form of planetary collapse. When a planet ventures too close to a massive object like a black hole or even another planet, gravitational forces can exceed the world's structural integrity. The side of the planet facing the massive object experiences stronger gravitational pull than the far side, creating tidal forces that can literally tear the world apart. This process, called spaghettification, when applied to black holes, can reduce entire planets to streams of debris orbiting their destroyer. Yet through all these mechanisms of destruction and transformation, matter itself remains conserved. The atoms that once formed planets don't disappear, they're recycled into new configurations. Stellar nucleosynthesis continues to forge heavier elements. Planetary formation processes continue to aggregate matter into new worlds, and the cosmic cycle of creation and destruction continues across scales from the molecular to the galactic. This perspective transforms our understanding of planetary collapse from simple destruction to cosmic transformation. Every collapsed world contributes to the enrichment of interstellar space, providing the raw materials for future generations of planets. Every ejected rogue planet carries with it the chemical legacy of its birth system, potentially seeding new regions of space with complex molecules. Every atmospheric loss from one world contributes gas and dust to the interplanetary medium from which new atmospheres might eventually form. The universe, in its patient way, seems to be conducting a vast experiment in organization and complexity. Planets form, evolve, and collapse, but each cycle produces new combinations of elements, new structural arrangements, new possibilities for complexity and even life. We exist not despite this cycle of destruction and creation, but because of it. Our own world formed from the debris of earlier stellar and planetary generations, and when Earth eventually faces its own collapse, its constituent atoms will join the cosmic recycling process that enables future worlds to form. In this grand perspective, planetary collapse becomes not an ending, but a transformation, not a failure, but a necessary step in the universe's ongoing exploration of what's possible. The cosmos doesn't mourn its collapsed worlds any more than a forest mourns fallen trees that enrich the soil for new growth. Instead, it patiently gathers the scattered pieces and begins again, crafting new worlds from old materials, continuing its billion-year project of complexity and beauty. So when we contemplate the various ways planets can collapse, we're not just cataloguing cosmic catastrophes. We're witnessing the universe's method of renewal, its way of ensuring that matter and energy continue to explore new forms of organization across the vast scales of space and time. So far, we've journeyed through the gradual collapse of planets through internal processes and catastrophic external forces, exploring how worlds transform rather than simply end. Now let's delve deeper into one of the most fascinating mechanisms of planetary destruction: the process by which entire planetary systems can spontaneously fragment and collapse through their own gravitational instabilities. When we think of planetary formation, we usually imagine the slow, patient accumulation of dust and rock over millions of years. But there's another pathway entirely, one that operates on timescales so rapid they make geological processes look glacial by comparison. This is the realm of gravitational collapse, where massive protoplanetary disks don't gradually coalesce into worlds, but instead fragment catastrophically, creating planets in cosmic instants. The story begins in the earliest epochs of stellar formation, when young stars are surrounded by massive disks of gas and dust. These aren't the thin, relatively stable disks we see around mature stars, but thick, turbulent structures that can contain as much mass as the central star itself. Under the right conditions, these disks become gravitationally unstable, developing spiral arms and density waves that grow stronger with each orbit. Think of it like a cosmic snowball effect. A small perturbation in the disk creates a region of slightly higher density. That region's stronger gravity attracts more material, making it denser still. The process accelerates until entire sections of the disk collapse into bound objects, not through the gradual accretion we're familiar with, but through direct gravitational collapse that happens in just a few orbital periods. This isn't theoretical speculation anymore. Recent observations of young stellar systems have have provided compelling evidence for gravitational instability in action. The AB Aurigae system, located some 520 light-years away in the constellation Auriga, serves as our cosmic laboratory for understanding these processes. This young system, only a few million years old, displays exactly the kind of spiral structure and density enhancements that theoretical models predict for gravitationally unstable disks. What makes AB Aurigae particularly fascinating is the presence of distinct knots and clumps embedded within its spiral arms. These aren't just density waves. They appear to be genuine gravitational-bound objects in the process of formation. Advanced observations using the Atacama Large Millimeter Array have revealed that the gas motion around these features shows clear signatures of Keplerian rotation, the telltale sign of matter orbiting a central mass. The implications are staggering. If these observations are correct, we're witnessing planets being born not through the slow accumulation of planetesimals, but through the direct collapse of disk material. Its planetary formation, in fast forward, compressed from tens of millions of years into mere thousands. But gravitational instability isn't just about rapid planet formation, it's also about rapid planet destruction. The same processes that can create worlds through disk fragmentation can just as easily tear them apart. When massive planets form through gravitational collapse, they often do so in unstable configurations. Multiple massive objects orbiting in the same system create complex gravitational interactions that can lead to ejections, collisions, or orbital decay. This brings us to one of the most sobering aspects of planetary collapse: the production of rogue planets. These are worlds that have been ejected from their parent systems, condemned to wander the galaxy in the cold darkness between stars. Current estimates suggest there may be billions, perhaps trillions of these wandering worlds in our galaxy alone, outnumbering the planets that remain bound to stars. The ejection process itself represents a form of planetary system collapse. When multiple massive planets interact gravitationally, the system seeks to reduce its energy by ejecting the least massive member. It's a cosmic game of musical chairs where there aren't enough stable orbits for all the players. Binary star systems are particularly effective at this process, with their complex gravitational fields providing additional perturbations that can destabilize planetary orbits. Recent simulations have shown that binary systems can eject an average of 2 to 7 Earth-mass planets, with the process happening most efficiently during the first few million years after formation. The ejected planets retain significant velocities, typically 8 to 16 kilometers per second, far faster than the typical motion of stars in their local regions. These high velocities serve as forensic evidence, telling us that these worlds were violently expelled rather than gently released. But the story of gravitational collapse extends beyond individual planetary systems to entire stellar populations. As stars evolve and change, they can trigger collapse events in previously stable configurations. When a star expands into a red giant phase, it can engulf inner planets directly. But even planets at safer distances aren't immune. The changing mass distribution and stellar winds can alter orbital dynamics in ways that lead to instability. The fate of our own solar system provides a sobering example. In about 5 billion years, our sun will begin its evolution into a red giant, expanding until it potentially engulfs the inner planets. Even if Earth survives the initial expansion, the changing gravitational environment and stellar mass loss will alter planetary orbits in unpredictable ways. Some planets may spiral inward to fiery destruction, while others might be flung outward into the cosmic void. This stellar evolution represents another pathway to planetary collapse, one that operates on astronomical timescales but with inexorable certainty. The nuclear furnaces that power stars have finite fuel supplies, and when that fuel runs out, the consequences ripple outward to affect everything in orbit around them. The most extreme cases involve massive stars that end their lives in supernova explosions. These cosmic detonations release more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. Any planets unlucky enough to be in the vicinity are instantly vaporized, their constituent atoms scattered into space to become part of the interstellar medium. Yet even in these moments of ultimate destruction, we see the universe's endless capacity for renewal. The heavy elements forged in stellar cores and dispersed by supernovae become the building blocks for new generations of stars and planets. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in the nuclear furnaces of ancient stars and distributed through cosmic explosions. This cycle of creation and destruction, collapse and renewal, operates on scales both intimate and cosmic. Individual planets may be destroyed, but their constituent matter lives on to form new worlds. Planetary systems may be disrupted, but the debris can eventually coalesce into new configurations. Even entire galaxies can collide and merge, triggering waves of star formation and planetary birth that compensate for the destruction. Perhaps most remarkably, we're beginning to discover that some of the most exotic remnants of stellar collapse can themselves become sites of planetary formation. Pulsar planets, worlds orbiting the ultra-dense neutron star remnants of supernovae, represent an extreme form of second-generation planetary systems. These worlds, forged from the debris of stellar destruction, orbit objects so dense that a teaspoon of their material would weigh as much as a mountain. The discovery of pulsar planets revealed that planetary formation can occur even in the most hostile environments imaginable. These worlds experience radiation levels that would sterilize any conventional life. Yet their very existence demonstrates the universe's remarkable ability to create order from chaos, structure from destruction. As we peer deeper into space and further back in time, we continue to uncover new mechanisms of planetary collapse and renewal. Some galaxies show evidence of massive black holes that have grown so large they disrupt star formation across entire galactic regions. Others display the aftermath of galactic mergers, with streams of stars and planets flung into intergalactic space. Yet for all the ways planets can be destroyed, through gravitational ejection, stellar evolution, supernova explosions, or tidal disruption, the universe continues to make new ones. Every collapse event that destroys existing worlds also creates the conditions for new planetary systems to form. The matter and energy released by destruction become the raw materials for construction. This cosmic recycling operates on timescales that dwarf human comprehension, yet it connects us intimately to the deepest processes of the universe. We are, quite literally, made of star stuff, the processed remnants of countless cycles of stellar birth, death, and rebirth. Our planet itself formed from the debris of earlier generations of stars, and when our Sun eventually dies, Earth's constituent atoms will be returned to space to participate in future cycles of cosmic construction. The collapse of planets, then, is not an ending, but a transformation. It's part of the universe's ongoing conversation between order and chaos, structure and dissolution, creation and destruction. In this cosmic dialogue, every ending enables a new beginning. Every collapse makes possible a new emergence. As we continue to study these processes, we're developing a deeper appreciation for the dynamic nature of planetary systems. They're not static arrangements, but living, evolving structures that respond to changing conditions over cosmic time. Looking at your script so far, you've done an excellent job exploring the multifaceted nature of planetary collapse. You've covered the internal processes, external forces, and the cosmic recycling aspect beautifully. For part 6, let's delve deeper into some of the specific mechanisms that drive planetary destruction, particularly focusing on the observational evidence and real-world examples that illustrate these processes in action. Now, you might be wondering, with all this talk of planetary destruction and cosmic violence, how do we actually know these things happen? How can we be certain that planets truly do collapse, fragment, and disappear into the vast darkness of space? The answer lies not in theoretical speculation, but in the quiet observations of astronomers who have spent decades watching the universe's most dramatic events unfold in slow motion across the cosmic stage. Consider the curious case of stellar evolution and planetary consumption. When stars like our Sun begin their final evolutionary dance, they don't simply fade away quietly. Instead, they undergo a dramatic transformation that can spell doom for any planets unlucky enough to be caught in their vicinity. As a star exhausts its nuclear fuel, it begins to swell, sometimes growing to hundreds of times its original size. This expansion phase, known as the red giant phase, is like a cosmic tide that rises slowly but inexorably, engulfing everything in its path. We've observed this process in systems throughout our galaxy. The star Mira, located about 420 light-years away, has already begun this transformation. Its outer atmosphere has expanded so dramatically that if it were placed at the center of our solar system, it would swallow not just Mercury and Venus, but potentially Earth as well. The star is literally shedding its outer layers, creating a spectacular tail of material stretching over 13 light-years behind it as it moves through space. Any planets that once orbited close to Mira would have been vaporized long ago, their atoms now scattered across interstellar space. But stellar evolution isn't the only planetary destroyer we can observe. Take the phenomenon of hot Jupiters, gas giant planets that orbit incredibly close to their host stars. These worlds, with names like WASP-12b and HAT-P32b, are caught in a deadly spiral. The intense gravitational pull of their stars stretches and distorts these planets, while the stellar radiation heats their atmospheres to temperatures exceeding 2000 degrees Celsius. We can actually watch these planets being slowly stripped apart, their atmospheres boiling away into space like steam from a cosmic kettle. WASP-12b, for instance, is losing approximately 6 billion tons of material every second. That's roughly equivalent to losing the mass of Earth's moon every 150 years. Telescopes have detected the planet's atmosphere extending far beyond its normal boundaries, creating a comet-like tail of escaping gas. Within the next 10 million years, a blink of an eye in cosmic terms, this planet will be completely consumed by its star, leaving behind only a faint trace of heavy elements in the stellar atmosphere. Then, there are the planetary collisions, events so violent they can reshape entire solar systems. 5 billion years ago, this collision was so catastrophic that it melted both worlds, sending a shower of debris into orbit around Earth that eventually coalesced to form the moon we see today. But we don't have to look to the ancient past to find evidence of such cosmic carnage. In 2009, astronomers using the Spitzer Space Telescope observed the aftermath of what appeared to be a massive collision in the BD Plutonium-20 307 system. The telescope detected an enormous cloud of dust and debris surrounding the star, far more material than should exist in a mature planetary system. The most likely explanation is that two large planets, perhaps each the size of Earth, collided at speeds of thousands of kilometers per hour, completely destroying both worlds and creating a debris field that will glow in infrared light for millions of years. Even more dramatic are the planets that face destruction from external forces beyond their solar systems. Imagine a planet peacefully orbiting its star, when suddenly, without warning, a massive object tears through the system like a cosmic wrecking ball. This isn't science fiction, it's the reality of galactic dynamics. Our own solar system travels through the Milky Way at a speed of about 220 kilometers per second, and occasionally we encounter other stars and their gravitational influences. The most spectacular example of external planetary destruction comes from observations of white dwarf stars, the dense remnants left behind when sun-like stars die. Many white dwarfs show signs of heavy element pollution in their atmospheres, elements like iron, magnesium, and silicon that should have long since sunk below the surface. The only way these elements can appear in a white dwarf's atmosphere is if they're being continuously replenished by infalling material. And where does this material come from? The shredded remains of planets. Astronomers have discovered entire planetary graveyards around white dwarf stars. The star WD 1145 plus Rome 17, located about 570 light-years away, is actively consuming a disintegrating asteroid or small planet. Telescopes have observed the debris creating a ring around the star, with chunks of planetary material periodically passing in front of the white dwarf, causing its light to dim in a chaotic, unpredictable pattern. It's like watching a planetary feeding frenzy in real time, but perhaps the most unsettling observations come from systems where planets simply vanish. The young star RW Aurigae A, located about 450 light-years away, has been dimming dramatically over the past few years. Initially, astronomers thought this might be due to dust clouds or other normal stellar activity. However, detailed analysis revealed something far more disturbing. The star appears to be consuming planetary material, possibly an entire planet that has been torn apart by gravitational forces. X-ray observations show the star's atmosphere is enriched with heavy elements, consistent with planetary destruction. The star has been literally eating its children, and we're watching it happen in real time. The planet's death throes are written in the changing light of its former sun, a cosmic obituary that telescopes can read from hundreds of light-years away. These observations paint a picture of a universe where planetary destruction isn't rare or unusual, but rather a fundamental part of cosmic evolution. Planets form, evolve, and are destroyed in an endless cycle that has been playing out for billions of years. Every star we see in the night sky has likely witnessed the birth and death of multiple worlds, and many of those stellar deaths have taken their planetary companions with them. What makes these observations particularly sobering is their implications for our own solar system. While Earth has remained relatively stable for billions of years, we exist in a dynamic, ever-changing cosmic environment. Our sun will eventually evolve into a red giant, potentially engulfing the inner planets. Asteroid impacts, while rare, could still pose a threat to planetary habitability. And on even longer timescales, gravitational interactions with other stars could disrupt the careful orbital dance that keeps our planet in the habitable zone. Yet there's something profoundly beautiful about this cosmic cycle of destruction and renewal. The atoms that make up our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in the hearts of stars and distributed through space by the very processes that destroy planets. We are, quite literally, made of star stuff that has been recycled through countless cycles of planetary formation and destruction. The destruction of worlds isn't an ending, it's a transformation. The carbon atoms that once formed the rocky crust of a planet billions of years ago might now be part of a living tree on Earth. The iron that was once locked in the core of a world torn apart by its dying star might now flow through the veins of a child taking their first steps. In the grand cosmic story, planetary collapse is not death, but metamorphosis, a changing of forms that allows the universe to continuously reinvent itself. This perspective transforms our understanding of planetary destruction from a source of cosmic dread into something approaching cosmic wonder. Yes, worlds die, but their deaths give birth to new possibilities, new configurations of matter and energy that wouldn't have existed otherwise. Now, let's trace the intricate threads that connect the distant past to the present moment, and explore how planetary death becomes the foundation for new worlds to be born. The universe, it seems, has a remarkable talent for recycling. When we speak of planetary collapse, we're not just discussing endings. We're witnessing the opening chapters of cosmic rebirth. Every shattered world, every ejected planet, every stellar catastrophe becomes raw material for the next generation of planetary systems. It's a process both violent and beautiful, destructive and creative, playing out across timescales that dwarf human comprehension. Consider the spectacular death of a massive star in a supernova explosion. The blast wave doesn't just destroy, it compresses nearby gas clouds, triggering the formation of new stars. The heavy elements forged in the dying star's core, from carbon to iron, are scattered across space, seeding future planetary systems with the very building blocks of rocky worlds. Without these stellar sacrifices, planets like Earth could never have formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the nuclear furnaces of stars that died billions of years ago. This cosmic recycling extends to planets themselves. When a star evolves into a red giant and engulfs its inner planets, those worlds don't simply vanish. Their material is dispersed into space, eventually becoming part of planetary nebulae that drift through the galaxy. These ghostly shells of gas and dust, illuminated by the dying star's white dwarf remnant, gradually mix with the interstellar medium. Future generations of stars will incorporate this material, creating new planetary systems enriched by the remnants of ancient worlds. Even more intriguingly, some planetary systems manage to survive their star's death and transformation. Pulsar planets, orbiting the dense neutron star remnants of supernova, represent perhaps the most extreme examples of planetary resilience. These worlds, bathed in intense radiation and gravitational waves, challenge our understanding of where planets can exist and how they can form. Some may be the remnants of planets that survived the supernova, their surfaces blasted clean and their cores exposed. Others might be entirely new worlds, condensed from the debris disk that formed around the pulsar. Either way, they demonstrate that planetary systems can emerge from the most violent cosmic events. The process of planetary ejection, which we explored earlier, creates another fascinating category of recycled worlds. Rogue planets, cast out from their birth systems during gravitational interactions, wander the galaxy like cosmic nomads. Current estimates suggest there may be billions of these free-floating worlds drifting through interstellar space. While they've lost the warmth of their parent stars, some may retain enough internal heat to support subsurface oceans, potentially harboring life in the darkness between the stars. These rogue worlds represent a form of planetary diaspora, carrying the chemical signatures and perhaps even the biological heritage of their original systems across vast distances. When they eventually encounter new stellar systems, they might be captured by gravity, becoming exotic additions to alien planetary families. Imagine a world that formed around a sun-like star, was ejected into the cold of space, wandered for millions of years, and finally found a new home around a red dwarf star. Such a planet would carry the geological and possibly biological history of two different stellar environments. The recycling process operates on multiple scales simultaneously. At the largest scale, entire galaxies merge and reshape each other, disrupting countless planetary systems and creating new ones from the debris. The Milky Way's eventual collision with the Andromeda Galaxy, predicted to occur in about 4 billion years, will likely trigger a massive reorganization of stellar and planetary systems. Some worlds will be destroyed in the chaos, but others will find new homes, and the enhanced star formation triggered by the galactic merger will create opportunities for entirely new planetary systems. At smaller scales, the migration of planets within their birth systems creates a constant reshuffling of cosmic real estate. The NICE model of solar system evolution suggests that the giant planets in our own system migrated significantly during the early history of the solar system, possibly triggering the late heavy bombardment that scarred the inner planets. This migration scattered countless asteroids and comets, some of which may have delivered water and organic compounds to Earth, contributing to the emergence of life. The concept of planetary collapse and rebirth also applies to the internal evolution of worlds. Planets undergo their own cycles of destruction and renewal. Earth's surface has been completely recycled multiple times through plate tectonics, with oceanic crust being continuously created at mid-ocean ridges and destroyed at subduction zones. The carbon cycle, operating over millions of years, has repeatedly transformed the atmosphere and climate. Mass extinction events have cleared the evolutionary stage for new forms of life to emerge and diversify. Mars offers a poignant example of planetary transformation. Once a world with a substantial atmosphere and flowing water, it gradually lost its magnetic field and atmosphere to space. The planet we see today is essentially the remnant of a more Earth-like world. Its surface carved by ancient rivers and its polar caps preserving traces of a more hospitable past. Yet even this apparently dead world may harbor life in its subsurface, and human exploration might one day transform it once again into a living world. The moons of the outer planets represent another form of planetary recycling. Jupiter's moon Io is constantly being resurfaced by volcanic activity driven by tidal heating. Its surface is literally being destroyed and recreated on timescales of thousands of years. Europa's subsurface ocean may be sustained by the same tidal forces, creating a potentially habitable environment beneath its icy shell. These moons demonstrate how gravitational interactions can maintain geological activity and habitability long after a world might otherwise have become dormant. Looking toward the future, the recycling process will continue on an ever grander scale. As the universe expands and cools, star formation will gradually slow and eventually cease. The last stars will be long-lived red dwarfs, shining for trillions of years. Around these final stellar beacons, the last planetary systems will form from the recycled material of countless previous generations of stars and planets. These final worlds will be the ultimate products of cosmic recycling, incorporating elements from the entire history of the universe. Even beyond the era of star formation, exotic processes might continue the cycle of planetary death and rebirth. Black holes, the final remnants of the most massive stars, slowly evaporate through Hawking radiation over unimaginably long timescales. The energy released in this process might, in principle, allow for new forms of structure formation in the far future. Speculative theories suggest that even in the deep future, when the universe is cold and dark, quantum fluctuations might occasionally create new pockets of complexity, new forms of organized matter that might, in some sense, be considered the descendants of planets. The story of planetary collapse and rebirth reveals one of the most profound truths about the universe. Nothing is ever truly lost, only transformed. Every atom in your body has likely been part of countless other structures throughout cosmic history. Perhaps in the core of an ancient star, the atmosphere of a primordial planet, or the tail of a comet. The universe is not just a collection of objects moving through space. It's a vast recycling system, constantly breaking down and rebuilding, creating new forms of beauty and complexity from the remnants of the old. This perspective transforms our understanding of destruction and creation. Planetary collapse is not an ending, but a transition, not a failure, but a transformation. The The universe doesn't waste anything. Every supernova, every planetary ejection, every stellar death contributes to the ongoing story of cosmic evolution. In this grand narrative, the collapse of planets is not a tragedy, but a necessary chapter in the endless book of cosmic becoming. As we stand on our own planet, looking up at the stars, we're witnessing both the past and the future of planetary systems. The light from distant stars carries the signatures of worlds that may have lived and died long before our solar system formed. The heavy elements in our planet's core were forged in stellar furnaces and distributed by cosmic catastrophes. We are not separate from this process of cosmic recycling. We are its products, its participants, and its witnesses. And so, after traversing the vast cosmos, from stellar nurseries to cosmic graveyards, from the gentle dance of planetary formation to the violent throes of stellar death, we find ourselves contemplating perhaps the most profound truth of all, that destruction and creation are not opposites, but partners in an eternal cosmic ballet. The story of planetary collapse, as we've discovered, is never really about endings. When a planet's atmosphere is stripped away by its aging star, those scattered atoms don't simply vanish into the void. They drift through space, carrying with them the complex chemistry forged in the heart of a world, until they find their way into new stellar nurseries. There, mixed with hydrogen and helium and the heavier elements born in dying stars, they become the building blocks of fresh worlds, new possibilities, new chapters in the universe's ongoing story. Consider the remarkable case of the white dwarf systems we've explored, where the ghostly remnants of once mighty stars are surrounded by the debris of their former planetary companions. These aren't monuments to failure, but treasure troves of possibility. The heavy elements polluting these stellar corpses tell us that somewhere, in some distant future, these materials will be recycled into new stars, new planets, perhaps even new biospheres. The carbon that once formed the backbone of organic molecules on a long-dead world might one day become part of a forest on a planet not yet born. This cosmic recycling extends beyond individual systems. The rogue planets we've discussed, those wandering worlds ejected from their birth systems, carry with them the geological and chemical legacy of their origins. They become interstellar messengers, spreading the products of planetary evolution across the galaxy. Some may even carry within their subsurface oceans the seeds of life itself, creating the possibility for biology to spread between star systems in ways we're only beginning to understand. The binary star systems that so efficiently produce these cosmic wanderers are themselves agents of renewal. Each planetary ejection event that seems so catastrophic from the perspective of an individual world is, from the galaxy's viewpoint, a distribution mechanism for complexity. The very instabilities that doom some planetary systems to collapse also ensure that the materials and patterns of planetary formation spread far and wide, increasing the chances that somewhere, somewhen, new worlds will arise with even greater potential for complexity and perhaps consciousness. Even the most violent planetary destruction events serve this greater purpose. When a massive star goes supernova and obliterates any planets in its vicinity, the explosion doesn't just destroy, it creates. The heavy elements forged in the star's final moments are scattered across light years of space, enriching the interstellar medium with the raw materials needed for rocky planets. The shock waves from these explosions trigger the collapse of nearby gas clouds, initiating new cycles of star and planet formation. What appears to be the ultimate cosmic catastrophe is actually the universe's way of ensuring that future generations of worlds will be richer in the elements necessary for complexity. This perspective transforms our understanding of planetary fate. The hot Jupiters spiraling into their stars aren't just victims of cosmic mechanics. They're participants in a process that will eventually lead to the formation of new stellar systems with different architectures, perhaps more favorable to the emergence of life. The worlds torn apart by tidal forces around their stellar companions contribute their mass to the evolution of those stars. potentially extending their lifetimes and creating new opportunities for planetary formation in their later evolutionary phases. The detection of second-generation planets around pulsars provides perhaps the most poetic example of this cosmic renewal. These worlds, born from the ashes of their predecessor planets, represent the universe's remarkable ability to create order from chaos, to build new complexity from the ruins of the old. They remind us that even the most extreme environments can give birth to new forms of planetary existence, new experiments in the cosmic laboratory of world building. As we look toward the future of our own solar system, we can find comfort in this broader perspective. When our sun eventually expands into a red giant and engulfs the inner planets, the Earth's story won't simply end, it will be transformed into something new. The elements that make up our world, including the carbon and oxygen and silicon that form the foundation of our biosphere, will be incorporated into the sun's outer layers and eventually dispersed into space. There, they will join the cosmic recycling stream, perhaps becoming part of worlds that will exist long after our sun has faded to a white dwarf. This cosmic perspective doesn't diminish the significance of individual worlds or the life they might harbor. Instead, it places each planet in the context of a much grander narrative, one in which every world, no matter how it meets its end, contributes to the ongoing evolution of the universe's capacity for complexity, beauty, and perhaps consciousness. Each planetary collapse is simultaneously an ending and a beginning, a death that enables countless future births. The universe, we might say, has learned to use destruction as a creative force. Through the violent dance of gravitational interactions, stellar evolution, and cosmic collisions, it continually reshuffles and redistributes the materials and patterns that make worlds possible. Every black hole that tears apart a passing planet, every stellar wind that strips away an atmosphere, every gravitational encounter that sends a world spinning into interstellar space. All of these apparent catastrophes are part of a vast, self-organizing system that maximizes the universe's potential for creating new forms of order and complexity. In this light, planetary collapse becomes not a failure of cosmic engineering, but evidence of the universe's profound creativity. It demonstrates that the cosmos is not a static museum of perfect, unchanging worlds, but a dynamic, evolving system that trades individual permanence for collective possibility. The very processes that doom some worlds to destruction ensure that the universe as a whole continues to grow richer, more complex, more capable of supporting the emergence of phenomena we can barely imagine. So when we contemplate the eventual fate of worlds, whether it's our own Earth facing the sun's red giant phase, or exoplanets we've never seen succumbing to the gravitational chaos of their birth systems, we can remember that we're witnessing not just an ending, but a transformation. The matter and energy that once formed those worlds will dance on through the cosmos, carrying with them the patterns and possibilities learned through billions of years of planetary evolution, ready to participate in the creation of new worlds, new stories, new chapters in the universe's endless book of becoming. In the end, planetary collapse teaches us perhaps the most important lesson of all, that in a universe governed by change, the most profound form of immortality isn't persistence, but participation in the ongoing creative process that makes new forms of beauty and complexity possible. Every world that has ever formed, no matter how it ended, has contributed something irreplaceable to that process. And in that contribution, in that gift to the future, every planet achieves a kind of eternal significance that transcends its individual fate. The cosmos, it seems, has found a way to make even endings into beginnings, even collapse into renewal. Now, Returning to the story of planetary collapse, we enter perhaps the most dramatic chapter in the cosmic narrative. Throughout this journey, we've seen how planets can be torn apart by internal forces, stripped of their atmospheres, or ejected into the cold darkness of interstellar space. But there's one more pathway to planetary destruction that deserves our attention. One that connects the smallest scales of the universe to the largest in a beautiful and terrifying dance of physics. Black holes represent the ultimate expression of gravitational collapse. These cosmic monsters are so dense that not even light can escape their grasp, and they demonstrate what happens when matter surrenders completely to the relentless pull of gravity. When a massive star exhausts its nuclear fuel, it can no longer maintain the delicate balance between the outward pressure of fusion and the inward pull of its own gravity. In a matter of seconds, the star's core collapses catastrophically, compressing matter to densities that boggle the mind. If the star is massive enough, this collapse doesn't stop at forming a neutron star. It continues until it creates a black hole. The formation of a black hole is itself a form of planetary system collapse. Any planets orbiting such a star would face an immediate and dire fate. The supernova explosion that often accompanies stellar collapse would first sterilize these worlds with intense radiation, stripping away atmospheres and scorching surfaces. But the real drama begins when the black hole forms and begins to interact with any remaining planetary material. Black holes don't just swallow planets whole like cosmic vacuum cleaners. Instead, they create one of the most spectacular and violent processes in the universe: tidal disruption. As a planet approaches a black hole, the gravitational field becomes so strong and so variable across the planet's diameter that different parts of the world experience vastly different forces. The side facing the black hole feels a much stronger gravitational pull than the side facing away, and this difference, known as the tidal force, literally tears the planet apart. The process is both beautiful and horrifying. The planet stretches like taffy, elongating in the direction of the black hole while being compressed from the sides. At first, the planet might resemble a teardrop, but as it gets closer to the black hole, it breaks apart entirely. The debris forms what astronomers call an accretion disk, a swirling maelstrom of superheated gas and dust that spirals inexorably toward the black hole's event horizon. This accretion disk glows brilliantly, heated to millions of degrees by the intense gravitational forces and friction. The light from this process can outshine entire galaxies, creating what we observe as quasars and other active galactic nuclei. In a sense, the destroyed planet becomes a beacon, announcing its demise to the entire universe. The very act of its destruction illuminates the cosmos, turning planetary collapse into cosmic art. But black holes don't always destroy planets directly. Sometimes, they capture them in stable orbits, creating some of the most extreme planetary environments imaginable. Planets orbiting close to black holes experience time dilation so severe that a day on the planet's surface might correspond to years in the outside universe. These worlds would be tidally locked, with one side perpetually facing the black hole and experiencing intense gravitational forces, while the other side faces the cold of space. The concept of planetary collapse extends beyond individual worlds to entire planetary systems. When galaxies collide, as the Milky Way and Andromeda are destined to do in about 4 billion years, the gravitational chaos can scatter planets from their orbits, sending them flying into intergalactic space. Computer simulations of galactic mergers show that a significant fraction of planetary systems are disrupted during these cosmic collisions, with planets either being ejected from their galaxies entirely or plunging into the central black holes. Even more exotic forms of planetary collapse emerge when we consider the universe's most violent events. Gamma-ray bursts, the most energetic explosions known, can strip away planetary atmospheres from distances of thousands of light years. These bursts, often associated with the collapse of massive stars into black holes or the collision of neutron stars, release more energy in a few seconds than our sun will produce in its entire lifetime. Any planet unfortunate enough to be caught in the beam of a gamma-ray burst would experience an instant and complete collapse of its atmospheric and possibly surface structure. The story of planetary collapse also includes the fascinating phenomenon of planetary migration. Through gravitational interactions with other planets or the protoplanetary disk, planets can spiral inward toward their star, ultimately meeting their doom in the stellar furnace. This process, known as Type 1 and Type 2 migration, explains why we observe so many hot Jupiters, massive planets orbiting extremely close to their stars. Many of these worlds are slowly evaporating, their atmospheres being stripped away by intense stellar radiation and winds. The ultimate planetary collapse scenario involves the far future of the universe itself. As the cosmos continues to expand and cool, stars will eventually exhaust their fuel and die. In the distant future, perhaps 10 and 100 years from now, even protons may decay, causing all matter to gradually disintegrate. In this scenario, planetary collapse becomes not just the fate of individual worlds, but the ultimate destiny of all matter in the universe. Yet even in these apocalyptic scenarios, the story of planetary collapse contains seeds of renewal. The materials scattered by tidal disruption around black holes can eventually be ejected in powerful jets, seeding the interstellar medium with heavy elements necessary for new planet formation. The planets destroyed in galactic collisions may find new homes in the merged galaxy, captured by different stars, or forming new systems from the gravitational chaos. The study of planetary collapse has profound implications for our understanding of life in the universe. Each mechanism of planetary destruction represents a filter that life must survive to persist and evolve. From the early bombardment that shaped the inner solar system to the future red giant phase of our sun, planetary collapse events have shaped the history of life on Earth and will continue to influence its future. As we stand on our own planet, contemplating these cosmic scales of destruction and renewal, we're reminded that planetary collapse is not merely an abstract astrophysical process. It's the engine of cosmic evolution, the mechanism by which the universe recycles matter and energy, creating new opportunities for complexity and perhaps consciousness to emerge. Every atom in our bodies was forged in the nuclear furnaces of dying stars, and every world we've discovered tells a story of formation, evolution, and eventual transformation. The dance of planetary collapse continues throughout the cosmos, a constant interplay between destruction and creation, chaos and order, ending and beginning. In understanding these processes, we gain not just knowledge of how planets die, but insight into how they're born, how they evolve, and how they contribute to the grand cosmic story of which we are all a part. So here we are, standing at the precipice of cosmic understanding, having traced the elegant dance of planetary formation and destruction through the dark reaches of space. We've witnessed how worlds can crumble under their own gravity, how stellar evolution can devour entire solar systems, and how the violent choreography of binary stars can hurl planets into the cold embrace of interstellar space. But perhaps the most profound realization isn't that planets can collapse. It's that collapse itself is merely another movement in the universe's endless symphony of transformation. Consider for a moment the beautiful paradox we've uncovered. Every act of planetary destruction carries within it the seeds of creation. When a red giant swallows its inner worlds, it enriches the surrounding space with heavy elements forged in stellar cores. When a supernova obliterates entire systems, it scatters the building blocks of future planets across vast cosmic distances. Even the violent ejection of rogue planets serves a purpose, distributing organic compounds and water throughout the galaxy, perhaps seeding new worlds with the ingredients for life. The white dwarf systems we've studied tell this story most eloquently. These stellar remnants, surrounded by the debris of their former planetary companions, aren't graveyards, they're recycling centers. The rocky material spiraling into these dense stars will eventually be incorporated into new stellar systems, reformed into fresh worlds that may one day harbor their own complex chemistry, their own atmospheres, their own possibilities for life. This cosmic recycling operates on scales both vast and intimate. The iron in your blood was forged in the nuclear furnace of a dying star. The calcium in your bones was scattered by a supernova explosion billions of years ago. The carbon that forms the backbone of every organic molecule in your body has traveled through countless stellar cycles, perhaps once part of a planet orbiting a long-dead star. You are, quite literally, made of recycled worlds. And this brings us to perhaps the most comforting truth of all. In a universe where planets can collapse, where stars can die, where entire solar systems can be torn apart by tidal forces, nothing is ever truly lost. Matter and energy are conserved, transformed but never destroyed. The complex molecules formed in the atmosphere of a doomed hot Jupiter don't simply vanish when that planet's envelope is stripped away. They become part of the stellar wind, eventually condensing into new planetary systems where they may play entirely different roles in the cosmic drama. Even the information encoded in planetary systems persists. The angular momentum of a planet ejected by gravitational interactions carries with it a record of its formation, its orbital history, its relationship with sibling worlds. The composition of polluted white dwarf atmospheres tells the story of the rocky worlds they consumed, preserving for billions of years the chemical signatures of planets that ceased to exist eons ago. These aren't endings, they're transitions. The gravitational instabilities that tear apart young planetary systems are the same forces that eventually sculpt stable, long-lived worlds like Earth. The stellar evolution that dooms inner planets also creates the heavy elements necessary for terrestrial planet formation around younger stars. The tidal disruption events that shred planets near black holes feed those same black holes, influencing the formation of galaxies and the large-scale structure of the universe itself. Perhaps most remarkably, the processes that destroy planets also create them. The same gravitational instabilities that can eject worlds from their birth systems can also trigger the direct collapse of protoplanetary disks, forming gas giants in mere thousands of years rather than millions. The shock waves from supernovae that obliterate nearby planets also compress molecular clouds, triggering the formation of new stars and their accompanying planetary systems. This cosmic recycling isn't limited to the distant past or far future. It's happening right now, all around us. Every day, our solar system sweeps up tons of interplanetary dust. Much of it debris from comets and asteroids that are themselves remnants of the solar system's formation. Some of this material may have originated in other stellar systems entirely, carried to us by the solar wind or the random motion of stars through the galaxy. We live within a constant flow of cosmic material, a gentle rain of recycled worlds. The exoplanet discoveries of recent decades have revealed this process in exquisite detail. We've found planets in every conceivable stage of formation and destruction, hot Jupiters spiraling into their stars, super-Earths with atmospheres being stripped away by stellar radiation, circumbinary planets navigating the complex gravitational dance of multiple stars. Each of these systems represents a snapshot of cosmic recycling in action, a moment frozen in the endless cycle of planetary birth, evolution, and transformation. Even our own Earth participates in this grand recycling program. The plate tectonics that drive continental drift and mountain building are essentially planetary recycling in action, constantly reworking the planet's surface materials. The carbon cycle moves atoms between the atmosphere, oceans, and solid Earth over geological timescales. The magnetic field that protects our atmosphere from solar wind erosion is maintained by the motion of liquid metal in the planet's core. Iron that was forged in the heart of a dying star billions of years ago. And looking forward, our solar system's future is part of this same story. In about 5 billion years, when the sun exhausts its hydrogen fuel and begins its transformation into a red giant, the inner planets will face their own cosmic recycling. But this isn't a tragedy, it's a continuation of the process that created us in the first place. The heavy elements that make up Earth and all life upon it will be returned to space, eventually becoming part of new worlds orbiting younger stars. Some of those future worlds may be even more conducive to life than Earth. They'll be enriched with heavy elements from billions of years of stellar evolution, possibly harboring complex chemistry from the moment of their formation. They may develop their own versions of plate tectonics, their own magnetic fields, their own protective atmospheres. And perhaps, in the fullness of cosmic time, they too will develop life, intelligence, and civilizations capable of looking up at their night sky and wondering about the fate of worlds. This is the ultimate message written in the physics of planetary collapse. The universe doesn't end stories, it transforms them. Every world that falls into its star, every planet ejected into interstellar space, every moon torn apart by tidal forces contributes to the ongoing narrative of cosmic evolution. The universe is not a machine that breaks down. It's a vast recycling system that ensures nothing valuable is ever permanently lost. So when we ask whether planets can collapse, we're really asking about the nature of change itself in the cosmos. And the answer is both humbling and hopeful. Yes, planets can collapse, stars can die, and entire galaxies can collide and merge. But from these apparent endings come new beginnings, new possibilities, new chances for the universe to explore what's possible. In the end, planetary collapse isn't the opposite of planetary formation. It's part of the same process, viewed from a different angle. Every ending enables a beginning. Every destruction makes creation possible, and every collapse carries within it the promise of something new. The universe doesn't just tolerate change, it thrives on it, using the energy released by every gravitational collapse, every stellar explosion, every tidal disruption to write new chapters in the ongoing story of cosmic evolution. And that story, we now know, includes us. We are the universe becoming aware of itself, matter that has evolved to the point where it can contemplate its own transformations. We are the cosmos looking back on its own history of planetary formation and destruction, recognizing in these processes not chaos or meaninglessness, but pattern, purpose, and an endless capacity for renewal. The planets may collapse, the stars may die, and the galaxies may fade, but the story continues, written in the language of physics and chemistry, told through the lives of worlds both real and yet to be born. And now, as we reach the twilight of our gentle exploration through cosmic collapse, we arrive at perhaps the most profound realization of all. The story of planetary destruction isn't merely one of endings. It's a testament to the universe's extraordinary capacity for renewal, transformation, and the emergence of something entirely new from the ashes of what came before. You see, when we think about planetary collapse, we often focus on the dramatic moments, the explosive ejections, the stellar consumption, the violent disruptions that tear worlds apart. But there's a quieter, more beautiful truth hidden within these cosmic catastrophes. Every act of destruction in the universe is simultaneously an act of creation. Every collapse a prelude to rebirth. Every ending the beginning of something we haven't yet imagined. Consider the humble elements that make up our world. The carbon in your body, the oxygen you breathe, the iron in your blood. None of these existed when the universe was young. They were forged in the nuclear furnaces of massive stars, scattered across space when those stars collapsed and exploded as supernovae. The violent death of ancient suns became the building blocks of new worlds, new life, new possibilities. In this sense, planetary collapse isn't just destruction, it's the universe's way of recycling, reimagining, and redistributing the materials of existence. When a planet is stripped of its atmosphere by stellar winds, those gases don't simply vanish. They drift through space, joining vast molecular clouds that will one day condense to form new stars and planetary systems. When a world is shattered by tidal forces near a black hole, its fragments become part of an accretion disk that glows with the light of transformation. Even the most complete annihilation of a planet becomes raw material for future creation, a cosmic phoenix waiting to rise from stellar ashes. The rogue planets we discussed earlier, those wandering worlds ejected from their home systems, carry within them the potential for entirely new forms of existence. Some may capture new companions during their cosmic wanderings, becoming the seeds of nomadic planetary systems that travel between the stars. Others might harbor subsurface oceans, hidden beneath frozen shells, creating isolated biospheres that evolve in splendid isolation throughout the galaxy. And then there are the second-generation worlds, planets born from the debris of their predecessors. These worlds inherit the heavy elements forged in stellar cores, making them richer in the building blocks of complexity. They can support more diverse chemistry, more intricate geology, and perhaps more elaborate forms of life than the pristine worlds of the early universe ever could. In a very real sense, planetary collapse enables the universe to become more interesting, more complex, more alive with each passing eon. The white dwarf systems we explored, where planetary debris rains down onto the cooling remnants of dead stars, represent another form of cosmic recycling. These polluted white dwarfs serve as archaeological records, preserving the signatures of destroyed worlds for billions of years. They're like cosmic libraries, holding the stories of vanished planets in their spectral lines, ensuring that even in death, these worlds continue to inform our understanding of planetary formation and evolution. Even the most exotic forms of planetary collapse contribute to this grand cycle of renewal. When planets spiral into black holes, they don't simply disappear into nothingness. Their mass energy contributes to the black hole's growth, and through Hawking radiation, even that seemingly permanent prison slowly returns its contents to the universe over unimaginably long timescales. Nothing is ever truly lost, only transformed. Perhaps most remarkably, the very processes that destroy planets also create the conditions for life to flourish elsewhere. The heavy elements scattered by supernovae don't just create new worlds, they make those worlds capable of supporting the complex chemistry that life requires. The gravitational disruptions that eject planets from their systems also sculpt the orbital architectures that allow other worlds to maintain stable, life-friendly environments for billions of years. This cosmic recycling operates on scales both vast and intimate. The water in Earth's oceans may have been delivered by comets, icy remnants from the outer reaches of our solar system that survived the violent early period of planetary formation. The very ground beneath your feet contains elements that were once part of other worlds, other systems, other chapters in the universe's long story of death and rebirth. As we've seen throughout our journey, the universe is neither cruel nor kind, it simply is. But within that vast indifference lies a profound creativity, a relentless drive toward complexity and beauty that transforms every ending into a new beginning. The collapse of planets isn't a failure of cosmic engineering. It's an essential feature of a universe that grows more magnificent with age. We're really asking about the nature of change itself in our cosmos. Yes, planets can collapse, and they do so in myriad spectacular ways. But their collapse isn't the end of their story. It's their transformation into something else, their contribution to the grand cosmic symphony that has been playing since the first stars ignited in the primordial darkness. In our own small corner of this vast universe, we exist because countless worlds before us lived, died, and gave their substance to create the stage upon which our own drama unfolds. And someday, far in the future, our own world will contribute its atoms to new stories, new possibilities, new forms of beauty we cannot yet imagine. This is the ultimate lesson of planetary collapse. That in a universe governed by change, destruction is not the opposite of creation, but its eternal partner. Together they dance through space and time, ensuring that the cosmos remains forever young, forever full of potential, forever capable of surprising us with its capacity for transformation. The planets may collapse, but the universe dreams on, weaving new worlds from the remnants of the old, painting fresh masterpieces on the canvas of space with brushstrokes of stardust and time. And in that endless creative process, in that cosmic cycle of death and rebirth, we find not cause for despair, but reason for wonder at the magnificent resilience of existence itself. So rest easy tonight, knowing that you are part of this grand cosmic story, made of elements forged in stellar hearts, living on a world that will one day contribute to futures beyond imagining. The planets may collapse, but the universe's capacity for beauty, for complexity, for life itself, only grows stronger with each turning of the cosmic wheel.